So that would be, what's that called again? The E, the beta particle. Put it there. Very good. So that's what happens to carbon-14. Electrons are produced when a neutron changes into a proton. Does everybody see that? Hello. This is the point here. It's a good point to make. You have a neutron up here that's going to change into a proton. Okay, that's what's happening. It's capturing the proton. The nucleus is capturing the proton, and it's ejecting an electron. This is coming off. So could it cause harm to you? It's an electron, yeah, possibly. It might degrade into something else, a gamma ray or something. We don't know. We know that the neutron itself is very unstable, and it decays into a proton and an electron. So we don't know how stable these are by themselves. It's emitting just one of them. So if they're grouped together in electricity, they seem to be a little more stable that way, because we transmit them from businesses, from the power plant to the business. All right, any question there? All right, who you gonna pick, Lauren?
Peace without truth.
Awesome, Claire. Well, say it again. I don't know if I got it totally. Take two. So can you say it again?
Oh yeah. Can't have peace without truth.
Excellent. Advisory. Okay, you're close. Does everybody agree with that?
Would it be positive?
Well, we're trying to make both sides equal. Close. No. Huh?
I think I know it.
All right, what is it?
Wait,
Positron emission. Come on up here, Heather.
am I right?
Maybe. Come up here and write it up there, you might be.
I'm not 100% sure how I write it though.
Well, actually, he's right now. Cody just changed his sign, so he's right. So it does release a hydrogen atom. Excellent. I was just concerned about his plus there. So that would be, what's that called again? The E, the beta particle. Put it there. Very good. So that's what happens to carbon-14. Electrons are produced when a neutron changes into a proton. Does everybody see that? Hello. This is the point here. It's a good point to make. You have a neutron up here that's going to change into a proton. Okay, that's what's happening. It's capturing the proton. The nucleus is capturing the proton, and it's ejecting an electron. This is coming off. So could it cause harm to you? It's an electron, yeah, possibly. It might degrade into something else, a gamma ray or something. We don't know. We know that the neutron itself is very unstable, and it decays into a proton and an electron. So we don't know how stable these are by themselves. It's emitting just one of them. So if they're grouped together in electricity, they seem to be a little more stable that way, because we transmit them from businesses, from the power plant to the business. All right, any question there? All right, who you gonna pick, Lauren? Okay, I think it's a 92, right? The 92 there? Yeah. The neutron breaks apart. It's a proton plus an electron. The nucleus captures the proton, it becomes nitrogen, and an electron is ejected, just like you see up here. That is correct. Got half of it right so far. Close, but no. You got half of it. You got like 6 plus 1 is what? 7. Now you have 14 over here, right? Plus 0 is 14. But you have 14 plus 1 is what? So what do you got to put over here? One, correct. So this actually is a hydrogen. So you're going to erase the E and you're going to put hydrogen because it has 1 proton and a mass of 1. Excellent. Excellent job, Brendan. All Brendan did was make sure both sides were equal. So what's 14 plus 1?
15.
What's 14 plus 1? Does everybody see how the 15 is the same? What's 7 plus 0? 7. What's 6 plus 1? 7, right? And then he went to the periodic table and he found hydrogen. So it emits hydrogen. Now this is a single hydrogen atom. It doesn't like being like this. It's diatomic hydrogen. It prefers to be H2. So it's going to aggressively try to find another hydrogen to bond with. So you might get 2 carbon 14s that decay at the same time. It might drive that. There might be some symmetry there.
Unstable nucleus and results in the formation of a stable nucleus. As figure 24.10 shows, uranium-238 first decays to thorium-234, which
Place this over here and here we place it over here.
Yeah.
It doesn't really matter. You could have placed this one there and this one there. It doesn't really matter where you place them. The important part here is that the mass stays the same. Mass is about accountability. Just like we said before about time, mass is associated with time. If there's always been mass, there's always been time. So it's very important for us to keep accountable to mass.
So this got to be 0. This is 1. What is this? This one.
All right, so you got 14 here, right? So that's right, that's 0. And then you're going to have,
Oh, a negative 1.
yeah. Now, let me see if that looks right.
I don't know what this part is though.
That's right. So that's going to be an electron. So you're going to put an E there. Excellent. You are correct. Good job, Jamal.
Radioactive decay. Won't they eventually disappear? Furthermore, isotopes have been decaying for about 4.6 billion years, the span of Earth's existence. Yet, naturally occurring radioisotopes are not uncommon on Earth.
Radioisotopes found on Earth. After all, if radioisotopes undergo continuous radioactive decay, won't they eventually disappear? Furthermore,
Carbon is what? Is it a liquid?
No.
It's a gas.
It's a gas.
It's a solid.
Oh.
It's a solid.
Often they call it black powder. Shh, you heard of black powder? Black powder is pure carbon. Now you can take black powder and you can make it into a diamond, which is pretty cool too. That would be an allotrope. Allotrope, where you have the same thing and you have different combinations of it, like O2 and O3, oxygen and ozone. So carbon is a black solid right here. When it undergoes decay, it becomes a gas and colorless, odorless. That's really kind of weird. It's like you were there and then now you disappear. Colorless odor. So this thing does happen.
Which in turn decays to protactinium-234. Decay reactions continue until a stable nucleus, lead-206 is formed.
Very good. All right, he wants to read the second paragraph. Radioactive decay. Note of these two, the positron emission and electron capture, because they're kind of the exception. How are they an exception? Well, this right here is supposed to designate the atomic number. What is the atomic number, Claire? What does the atomic number tell you? No. Starts with a P. Yeah, it tells you the number of protons. Well, unfortunately, this is an electron. So if you look over here, this is an atomic number, this is an atomic number. Is everybody clear? That's how you go to the periodic table to figure out what's going on. This is an atomic number, atomic number. No atomic number, 0, right? Well, you can have a positive, which actually means a 1. But unfortunately, this is not an atom. An electron is not an atom, right? It's not a proton. So you have to put the positive there. The positron one is the most difficult one to kind of, you almost have to just memorize what they're doing. Don't forget the positive. Now, the important part of these two is understanding the mass. Why is mass important, Lily? Close. Because that's when time begins. Remember we talked in the beginning of the year, mass. If you have mass, you have matter, and you have time. So mass is what we really want to focus on as being important because it gives us validation. What do you mean validation? Well, when events happen, they're based on mass. Like if you go do something, a record of that event occurs and people document it, and then if you did something wrong, they put you in prison, right? Or you get set free, one of the two. Or if you're doing good events, then you get paid more money, right? Make sense? So mass is what is very important. So you always want to follow the mass to justify the reaction.
Life for 1/2 of a radioisotope's nuclei to decay from its products. For example, the half-life of the radioisotope strontium is 29 years. If you had 10 grams of strontium, 90 today, 29 years, you would have 5 grams left. Table 24.4 shows how this decay continues through 4 lives of plutonium-90. Figure 24.11 presents the data from table in terms of percent.
Write this down. First thing I do is write down it's Krypton 85. So you don't keep rereading the problem. You can do math problems when you see it like this, so it's easier just to write it like this. Pull the information out of the word problem. So the half-life is 11 years. The amount given is 2 milligrams after 33 years. And then they want to know what amount remains. So the formula you're going to use is on the sheet that I gave you where it says N equals N sub O 1/2 exponent N. So we're going to place 2 milligrams in for the amount given, N sub O. Half is the half-life. Basically when you're talking about like the half-life is 11 years, there's a 50% chance half of it will change in 11 years. You might want to write that down if you didn't get that. Half-life means there's a 50% chance that half of it will change in 11 years.
The radioisotope strontium-90 is 29 years. If you had 10 grams of strontium-90 today, 29 years from now, you have
Where it says Krypton. $85.
In the formation of a stable nucleus, as figure 24.10 shows, uranium neg-238 first decays to thorium 234, which in turn decays to how do you say that? Protactinium. Okay, decay reactions continue until a stable nucleus when it leaves 206 is formed.
Okay, very good. So we're talking about radioactive decay now. What does half-life mean, raise your hand? Trey?
Each time required for 1/2 of the radioisotope's nuclei to decay its products.
Very good.
Natural occurring radio found on Earth after all radio, how do you say that?
Isotopes?
Oh, this isotopes underground continues radioactive decay. Won't they eventually disappear? Furthermore, isotopes have been decaying for about 4.6 billion years. This span
Strontium.
Strontium-90. Figures 24.11 Neg a radioisotope nucleus. nuclei to decay into its product.
You don't know.
Nice job, Chelsea. Now you gotta pick somebody to do number 2. Alexis? Very good. No, it's not calcium, it would be uranium U.